In a previous series of videos called Demystifying the Ferrocell, I showed you how the light lines that you see in the ferrocell are caused by reflection off the nanoparticles within the ferrolens. So using the law of reflection only, we are able to reconstruct the light lines in a computer simulation written by AB Science. So as you can see, the replication is very good. Really all we're concerned about here are the trajectories of these light lines and not any other optical effects that are going on within the glass and the fluid between the glass itself. So here is a schematic of the experimental setup. We've got the ferrolens right here, and what we have, the ferrolens is made up of two optically flat pieces of glass with a thin film of a ferrofluid diluted with some lubricant of some sort. I use baby oil, others use mouse milk, and even others use WD-40 or a combination thereof. So this is the ferrolens right here. Here is the magnet. In this schematic I have two light sources, one here and one here. In the observer, the eye, the camera, or whatever we are using to look at the ferrocell is in some other location. Okay, so let's just have a look. Let's have a look at a more realistic setup here. This is actually the ferrolens right here. We've got the ferrolens and we've got the magnet, and we've got the two light sources that I showed before. So the idea here is that the light is being emitted by the LEDs, and it is entering the ferrolens from here and wherever the light source is. So in this case, the light source is here and here. The light is entering the ferrolens and reflecting off the nanoparticles that are in between this very, very thin layer of fluid between these two optically flat pieces of glass. And so as you can see, the light is going to enter the lens and it's going to maybe reflect off a particle here, and it is going to potentially enter the eye, or it might enter a region of the fluid, of the particles within the fluid, and reflect away from the eye. So the eye will only see, of course, the light that reflects towards the eye, and it will not be able to see the light rays that are projecting away from the eye. So what is actually going on inside this thin region, inside the space between these two pieces of glass? Well, in the presence of a magnet, what happens is the particles line up, they clump together, and they form these needle-like filaments, and they align with the magnetic field of the magnet, whatever the magnetic field happens to be in this region of space. So this region here corresponds to a very small region. When you take the measurements of these filaments, actually when you use a medium-sized magnet, you've got, so this line here is 100 micrometers. So these little filaments are around 100 micrometers long, and of course with a stronger magnet, a 300 Gauss magnet, the filaments elongate quite a bit. They get a little thicker and they get a little longer, but basically you can see that this region here, or this region here, is really maybe a few hundred micrometers in width and height. So this is a very small region. Now if you were able to see the whole ferrocell, if you were able to see all of the tiny little nano needles aligned. If you had a whole bunch of them and you were to see them aligned, it might look something like this. So this is a 3D model that I made and I showed in a previous video, and you could see that this is a very thin layer. What I'm doing is simulating a very thin layer of the ferrocell. So this thin layer right here. Okay, so let's go back to this. So this thin layer right here is the same as this thin layer right here. And so you can see, I'm going to actually zoom in on that so you can see the needle structures in my model. Now this is of course an ideal model. It's not in this ferrocell here. You can see that the nano needles are a bunch of different sizes. They're not all the same size, and in my model they are they're all approximately the same size, and you can see how they are oriented depending on where they are relative to the magnetic field. Now in this model, the magnet was right in the middle here. Okay, and so so I generated this 3D model of the space between the two pieces of glass. And as you can see, this is not, although when you look at it from far away, it looks very, you know, two-dimensional, almost exactly two-dimensional. It is a very thin slab, but in reality it is a 3D model by definition, because the particles can align themselves out of the plane, and they do align themselves out of the plane of the ferrocell, of the very center of the ferrocell. So this is what it would look like. This is what this would look like in the ideal situation where you had a whole bunch of nanoparticles that are aligned with the magnetic field of the magnet. And this is the image that you see in the polar view of the magnet when it is oriented this way. So in the ferrocell, this is what you see when the nanoparticles are aligned as I do in this model. So what you see when you look at the ferrocell is highly dependent on where you place the magnet relative to the ferrocell, and where you place the lights relative to the ferrocell, and where you place the eye relative to the ferrocell. Okay, so what I'm going to do is I'm going to show you a movie of what it looks like when you change the position of the eye. Okay, so here is a video I made. I am moving the camera around to different views, and I am tilting it to away from the camera, and you can see that the light lines that we see, I'm just going to stop it right there. The light lines that we see are when you're looking at it on an angle where the lines cross, etc., is quite a bit different than when you're looking at it face on. Okay, so when you move the camera around, you see something different than what you see when you are looking at it straight on. Okay, so camera view is extremely important. The position of the eyes is because you only get to see the light that is reflected to your eye. Okay, so if there are no light rays going to your eye, you're not going to see any light. And of course, that's not the case. Of course, many light rays are going to your eye, and many light rays are moving away from your eye, and you are seeing only the light that is projected to your eye. Okay, so now I'm going to show you what it looks like when you move the magnet around. Okay, when you move the magnet, let me go back to my other model here. When you move the magnet around, okay, you're going to see different things happening compared to when you don't move the magnet around. So here is that video I did it first. This one I did first with, I'm actually moving the ferrocell relative to the magnet. So I'm moving the ferrocell instead of the magnet, but the relationship between the magnet and the ferrocell is changing. And now I'm doing the same thing with the simulated software. And you can see that it is behaving exactly the same as the original animation, or as the original video. So let's look at this one more time. I'm moving the ferrocell around relative to the magnet, and in the simulation I am going to move the magnet around relative to the ferrocell. Okay, so as you can see, it is very important to, when you're doing these simulations, it's very important to know where the magnet is, where the ferrocell is, where the lights are, okay, and where the camera is, where the eye is, where the detector of the light coming, reflecting off the nanoparticles between these two pieces of glass, how does that light get to your eyes? And that is what the simulation that AB Science developed does. Okay, he projects the light to the camera, intersects a plane, and displays what you would see in this experimental setup. So next, what I'm going to do is I'm going to critique a couple of videos by a YouTuber that goes by the name of MARKOUL11. Okay, so the last two videos he did are called Magnetic Flux Looping Between the North and South Poles of a Magnet, and Review of New Ferrocell Display Misconceptions. Now I'm going to do this one first because that is the second last video that he presented. And in fact, he is critiquing my video in his video. And so I am critiquing a video of a critique of my video. So let's first hear what he has to say.
Hello, I am Emmanuel Markoulakis from the Hellenic Mediterranean University. I'm doing this video because some creators of YouTube have come with some new information about what the title is, the center title concept is, what the ferrocell really shows. And in my opinion, they present some incorrect information from my research. And it's a good thing, I remind everybody, that when people which are not immediate experts on these fields, academic experts on these fields, doing such kind of videos, it's always a good thing to state that these are all under their opinion, yes, and exactly the same I'm stating also here, that this is my opinion, okay. I don't mean to have any misconflict with anyone, yes, but I am obliged, because my research, all these years, my experience, to set some things straight.
Okay. So first of all, he states that the work that AB Science and I are presenting are incorrect. Of course, he also states that that's his opinion. He also claims, or he also assumes for some reason, that neither of us are immediate experts in the field. He never took the time to check to see if either of us had any academic experience, and so I can tell you right off the top that although my area of expertise isn't, I'm not an immediate expert in this field, AB Science is. He is 100% an immediate expert in this field, and I'm pretty sure that Emmanuel here knows that. Okay, so I think it's a little disingenuous for him to say that. The other thing I want to say is that I say, in my opinion, all the time. In so many of my videos, I've said, in my opinion, in my opinion, in my humble opinion. I use IMHO in a lot of my comments, which means in my humble opinion. So everything I say, just for the record, Emmanuel, everything I say is in my opinion. Everything. I'm not saying anything as fact. I'm not stating anything as fact. All I'm doing is stating my opinion and showing my evidence. And that's what a good scientist does.
So we will now see what is presented. I use material from the video of these creators, but this is under fair use because I'm reviewing this material. So they use classical analytical electromagnetic theory and simulate magnetic moments here, visualize magnetic moments, where we have here rods which are aligned to external magnetic field, and here we see actually the alignment of these rods under an incident field of a pole of a magnet. So the lines are going all in here in the center point, they dive in, and therefore also the ferrocell has, because these lines are becoming here vertical, they minimize the surface and the light scattering is now minimum, and therefore also the ferrocell depicts these areas as black, this area. So here is the torus, which is formed from the polar field of a magnet of one pole. And we see here all the moments here of these nanorods going in. The same is actually happening on the ferrocell, which has nanoparticles, 10 nanometer in size, and they're forming a few hundreds of nanometers of these rods, nanoneedles or nanorods. However, here the creators say that this film is very thin. This is true. This is 10 microns thin, and therefore from there they imply that this is actually only a 2D surface, which is true to some extent, that it's a 2D cross-section.
Okay, so technically I am not implying that this is a 2D surface. Okay, I never ever implied that. This is not a 2D surface. Obviously, as I stated a few minutes ago, this is a 3D volume that happens to be really, really thin. Okay, this is a 3D model, not a 2D model. Even though it is almost 2D, it is not a 2D surface by any stretch of the imagination. Mathematically, this is still a 3D model, and you can see that these nanorods are pointing in a direction that is, orthogonal to this two-dimensional surface in most cases. And along the edge, of course, they are going to be pointing in different directions, but the point is that Emmanuel is mistaken, that I never implied that this is a 2D surface. This is definitely and 100% accurately explained as a 3D model.
Projection of the field, of the incident field on the ferrocell surface, but there is some difference because the nanoparticles are 10 nanometers and the thickness of the film, of this thin film of nanorods, is 10 microns. So actually for a 10 micron thick ferrocell film, which is a superparamagnetic film, an analogy is a man 2 meters in height, and the whole thickness of the film is 2 kilometers. It's 1,000 times more. It's the nanoparticles are 10 nanometers, and the thickness is 10 microns. So it's 1,000 by a factor of 1,000. So this is not to scale. So you will now imagine that there is actually plenty of room here to actually, yes, it is a 2D, it is a compressed field from 3D to 2D, but actually there is plenty room to make an imprint, a 3D imprint, compressed of course to 2D, but not exactly flat 2D as we have in the iron filling experiment. So it's a compressed 3D field into a 2D. It tries to make a 2D compression, but it's not totally 2D. You can't actually compress here this 3D field in this 3D space. So it's macroscopically, yes, it's 2D for an observer, but for the particles, from the reference point of the particles, of the nanoparticles, the 10 nanometer inside particles, there's plenty of room to compress the whole 3D field here in this 3D space.
Okay, so I'm not exactly sure what he's talking about here. As I said before, my model is a 3D model, not a 2D model. And here he's talking about not to scale, but the mistake that he's making is the fact that these nano needles are not in the order of nanometers, they are in the order of micrometers, okay? And so his not to scale argument falls apart because this is actually from the paper Horocycles of Light in a Ferrocell, which I highly recommend because it's got a lot of pretty pictures in it and it talks a lot about the Ferrocell. And this is by Alberto Tufel, Michael Snyder's on this paper, and Adriana Tufel. And so I'm not really sure what he's talking about here in terms of not to scale, because the numbers that he's quoting are not to scale in terms of what is actually observed under the microscope. Okay, so that is a big mistake that he's making in his assessment of the not to scale problem. Not to scale is not a problem. And somehow he is thinking that the whole magnetic field of the magnet can get compressed or squished into this thin, tiny layer between the two pieces of glass. And I'm not 100% sure where that comes from, because clearly in my model here, the magnet is way over here, and the ferrolens is right here. Okay, let's look at my schematic. So the ferrolens is here, and the magnet is here. And so I'm not really sure how he can think that the whole magnetic field can be somehow projected to that very thin layer of the fluid within the magnetic field, when the ferrolens is only going to be intersecting. So this this layer right here, this thin layer, is only going to be intersecting a very thin layer of the magnetic field that's generated by this magnet. The whole magnetic field cannot fit in this tiny thin layer here. So this diagram that he's drawing here is very confusing. I'm not entirely sure what he's talking about here.
So keep that in mind as the first point. So the field now is here. It's not really 2D, but it is compressed. It's a 3D field compressed in a very thin layer, but still it has a third dimension. Yeah? And that's why the ferrocell, we will see later, please stay with me, we will explain everything, has also retained steps of field information together with magnetic transparency, which is very important to understand what the ferrocell shows is exactly what is predicted by theory. We will prove that in a few minutes. So input at this specific simulation used is correct because first, the density here is too large, it's ridiculous large. In a normal ferrocell, the volumetric percentage of the nanoparticles compared to the solution which they're in is 0.2%, 0.2%. It's very high here used, and we cannot know the exact paths of the trajectory the nanorods are taking, because you see the nanoparticles, which are spherical, are joining and forming these nanorods. The nanorods are about a few hundreds of nanometers long, but the nanoparticle itself are only 10 or less nanometers. So we don't know exactly what the trajectory is, the path they are taking, because the simulation seems to input classical magnetic moments, and I'm not sure if the simulation also takes into account the magnetic anisotropy of the nanoparticles, which then will give different field pattern. So the density is too high, so the simulation is not correct.
So the density really has nothing to do with it. In our actual simulation, what we do is we take every point in the field of view and assume there is a nanoparticle there, and then we align it to the magnetic moment, and then we decide whether we can see it or not. So the density of the particles really makes no difference here. That is really kind of a moot point, because the way we do our simulation is dependent on the orientation of the magnetic moments, not the quantity of them, nor the density of them. Okay, so that is definitely a moot point. The density of these particles has nothing to do with the simulation that we're doing.
We have also take this into account. We see here a video of the nanoneedles inside the ferrofluid, how they align to an external magnetic field, and also the light scattering effect. But we are not sure, we cannot be sure about we can zoom in individual nanorods, but we are not sure about the final trajectory the magnetic flux lines are taking inside the ferrofluid. And yeah, so the simulation therefore is under question. But in general, yes, the lines are going this direction to the center of the pole. So we have the pole now under here, under the surface. Here is the center of the pole of the magnet, and the lines are going this direction. But again, we are not sure if this is the exact pattern, and if it doesn't make any other trajectory, the lines here, because having so much dense nanorods simulated and in that large size makes the behavior of the ferrocell now more to the macroscopic side, which means that there is a lot of coherence. And we know that the nanomagnetic thin film of the ferrocell has a quantum behavior.
Modeling the nanoparticles using only magnetic moments, and we're getting very accurate results regarding the location of the light lines, tells me that there's not much else going on there that we need to worry about, because we are very accurately mimicking those light lines that we're seeing, and we don't need to look further because the simplest solution, of course, is the best solution. So we don't need to assume that there's something different going on at the nanoscale as is going on at the macro scale.
Actually, also they shouldn't have. It was not needed to use all this simulation by MacPython, the program. They could have used just a solid surface torus. The effect will be the same. The LED illuminating the surface of the torus. So here is now the image under question. They make here, the creators of these videos made a side-by-side comparison of the actual display of the ferrocell with a magnet pole under the ferrocell and one light source on the perimeter with what they get from the blender simulation, let's say so, yeah? So what they actually did is they shifted here the blender image, they displace it in order to match to the left here, the displays to the left, to match what we see here on the actual image of the ferrocell. Of course, with one LED source, you will not see anything of that image here, displayed of the ferrocell. Thanks God, the light here is diffused on the perimeter of the cell, and that is the only reason you can see this. Because if it was just one light source, I assure you, you will not see anything of this loop here.
Okay, so I can debunk 100% what he just said there with this image here. Okay, so with this image here, what you see is a laser light source here. You see a laser light source here. And you have a brightened region here. So you have a laser light source here. You can see the path of the light here, but you can also see that there's a huge reflection on this side, and you can see a pattern forming, a similar pattern, maybe not as strong as here, but you can see another one forming on this side, and this is caused from this, as if this is a light source. And of course, this here is a lot more diffuse than this one here, but I don't really know how he can say that this light here is caused from this light here, because this is definitely not bright enough to do anything. Okay, he's saying that the light from here is coming into here and reflecting off to here and into our eyes. So I don't buy that. I don't buy that whatsoever. And the fact that our simulations, shows the light path taking the same path as what we're seeing here tells me that it really has nothing to do with what's happening at the perimeter, unless of course the light, if the light coming over here reflects that back like that, like we're seeing here. So this light here is causing a similar kind of a thing going on here, but it's not really bright enough to, it's more diffused than this one here. But I can't really, this is not really bright enough, in my opinion, in my humble opinion, to be causing this curve right here. Okay, and so I don't think what he said about the perimeter causing these reflections is correct.
Automatically, we can say it is a magnetic line of force. It cannot be anything else. But it is all a matter of understanding how the field is compressed on the 10 microns thickness of the cell.
Okay, so again, he's talking about how the field is compressed to the 10 micron thickness of the layer between the two pieces of glass. Somehow he's saying that the whole magnetic field of this magnet is compressed to this 10 micron thin layer, between the two pieces of glass. Okay, so I don't quite understand what that means.
Yes, how the 3D image is compressed in this thickness, and how it is projected. It's very important. As soon as you understand these two things, you will see that actually the ferrocell depicts exactly what is predicted by theory.
Okay, so I agree that the ferrocell displays exactly what's predicted by theory in terms of the magnetic moments and the way that light reflects off of reflective surfaces. So, I agree that standard physics, normal physics can explain these things. So I'm not really sure what kind of physics he's talking about, because I don't think it's really necessary to invoke some sort of a compression of the magnetic field but into a 10 micron thick layer to get this to work.
So this line now here, this is actually a loop. Remember I told you that when you see the field in the ferrocell, even with this single light source, which again I say it's wrong, you need homogeneous 360-degree lighting. Every magnetic line or loop must be illuminated from all angles, else you can make wrong conclusions. But for the sake of the argument, I will use just this experiment to prove that even with this experiment, with this single loop, the ferrocell shows correctly the field.
Okay, so he's saying that the ferrocell is showing the field. It's showing a magnetic field. So this is his opinion, his hypothesis is that the ferrocell is showing somehow showing the magnetic field.
So remember that I said that the ferrocell shows a depth of field information. So this is not just flat here in a 2D parallel surface, but it's going in it.
No, the ferrocell does not show depth of field at all. It can't show depth of field because it is a very thin layer of the very thin layer of ferrofluid between two pieces of glass, and the depth of field could only be one thing, and that is an optical illusion.
It is inclined here, so it shows depth of field. And in the
now it looks like a depth of field. It looks like a depth of field as much as a hologram looks like it has a depth of field. So this would be more analogous to a hologram than it would be to an actual depth of field.
Time has also magnetic transparency. When you see the magnetic field and magnetic flux of lines, magnetic flux lines on a ferrocell, you see the lines going through both around and through both of the poles of the magnet. So this here, what you see actually here is this here. So here is the ferrocell, and we have put a pole of the magnet under and perpendicular to the surface of the ferrocell, a pole of the magnet here. And what this here represents going around is one loop here.
So basically what he is saying, and if I understand it correctly, this loop here corresponds to this loop here, or a loop through the magnet. Somehow this loop here corresponds to this loop here. So he also said earlier on in the video, when he was talking about the not to scale stuff, he was talking about how the field is compressed. Okay, so he is wanting to compress this three-dimensional field into a very, very flat, thin plane that lives in between the two pieces of glass in the ferrocell, in the 10 micron thick space in the fluid between the two pieces of glass. So this is what he appears to be doing. Okay, so that is like saying, so here's my setup here. I rotated it, so now the ferrocell is sitting this way. Here is the magnet, here is the table, here is the thin layer between the two pieces of glass. And so what Emmanuel seems to be saying is that instead of this, okay, so here is my magnet. here is what the field would look like, okay, around the magnet. And in my world, the ferrocell, the center of the ferrocell, the surface of the center of the ferrocell will intersect the magnet, the field, will intersect the magnetic field at this location, and the nanoparticles will self-organize into tiny nanoneedles and align along the magnetic field lines in this plane that intersects the magnet. Okay, so that's what happens in my world. What Emmanuel wants us to do is he wants us to squish this and put it right here. Okay, that's what he's doing right here. And even worse, he wants us to squish it until it fits inside this tiny 10 micron thick, thin layer between the two pieces of glass. And so that seems a bit strange. I'm not really sure why we need to do that when it makes more sense to place the magnetic field here and then take the intersection of where the center of the ferrocell intersects the magnetic field of the permanent magnet that's sitting right here, and that is that causes the nanoparticles to align, and that causes them to to self-organize into this pattern. So this pattern is actually this same intersection point. So when I made this model actually intersects at exactly this point here, about approximately 3 millimeters above the surface of the magnet. And of course, when you do that, you get this image of the ferrocell. And so I don't think I need to go any further. There's something definitely very strange about this compression, using this compression as a reason for why the ferrocell looks like this. I think it's actually much simpler to say that the magnetic field, wherever you place the magnet relative to the ferrocell, the magnetic field, wherever it intersects, let's say I do, let's do this. So let's say instead I put the magnet like that. Okay, so this ferrocell is going to intersect different lines of force, and it is going to create a different pattern depending on where I place the magnet. As I showed you, when I move the magnet around, you get a different picture. Okay, when you move the magnet around, you get a different projection. What is projected to your eye is, changes, right? And so that seems like a much simpler explanation for what we see in the ferrocell than some complicated idea of compressing the magnetic field, so 3D magnetic field into a 2D structure, and then place that between the two pieces of glass. That doesn't, make any sense at all. It also doesn't make any sense to say that this is this. It doesn't make any sense to say that this line that we're seeing here is a magnetic line of force that passes through the magnet. There is no reason to say that. There is no evidence that this is true. It is doesn't even make sense in terms of logic and in terms of geometry of 3D space. This is a strange idea. It doesn't really make any sense. This is also what he's trying to say in this other video called magnetic flux, looping between north and south poles of a magnet, clearly shown by the ferrolens. Now this is interesting because this is something that I kind of was investigating a while back, and I've got this little toy called the toro flux, and in this toro flux you've got these little lines that loop around in a circle, and I did remark at how much this looked like the ferrocell, okay? But this again is not physical reality. You shouldn't be taking reflected light from the ferrolens to represent physical reality. It is no better than taking a shadow and putting physical reality, extrapolating physical reality from the shadow. Okay, so this is, I believe, what he's trying to get at in this second video. In this video where he shows the toroflux and the ferrocell side by side. So I hope this helps in demystifying the misconceptions of the misconceptions that were presented in this video. So ironically, the review of the new ferrocell display misconceptions were actually based on misconceptions. What's actually going on here is that we've got the magnet right here, which has a magnetic field, and the magnetic field intersects the ferrolens, intersects the center of the ferrolens, and the light from the LEDs enters the lens and reflects off the tiny nanoparticles that are aligned with the magnetic field only in this plane, and then the light gets reflected off the nanoparticles, and some of the light reaches our eyes, and we see the famous patterns that we see. So that's about it. I'm going to leave it at that. This video is already long enough as it is, so I'm just going to say ciao for now.